Hey everyone, and welcome back to Physics 101. Today is our first chapter on our series on physics, and it is on motion. Motion is a very fundamental concept, one of the basics, and it is one of the first things you'll learn in any physics course. So let's get started. We're going to start with the four definitions on the left here: speed, displacement, velocity, and acceleration. We're going to start with speed. So speed, everyone knows what speed is. We have the definition as distance traveled per unit time. Well, that makes sense. If you go from point A to B in a short amount of time, you're going fast. If you take a long time to get there, you're going slow. Right. Well, I've listed this definition here because we need to find its relationship to velocity. Speed and velocity are often considered the same thing, but as we'll see, they are not exactly the same. We have the definition of velocity as the rate of change of distance. This is quite similar to the definition of speed, but as we know, they are not the same thing. This is because speed is a scalar and velocity is a vector. So speed being a scalar is only going to have magnitude, and velocity as a vector is going to have magnitude and direction. This is important because in physics, direction is quite important. Um, um, so that is why you're going to see the word velocity a lot and the word speed not very much. I have not seen the word speed in a physics problem or in a textbook for a long time, and that's because we almost always deal with velocity as it has direction, and direction is quite useful to know, quite important. Now, on to displacement. We have the definition here. It's an object's change in position, measuring from starting to final position. Now, if you haven't really caught on yet, like speed and velocity, displacement has a relationship with distance. Distance being the scalar, displacement being the vector. So let's make an example here, just an example problem. Let's say I start at point A and then I walk 10 meters to point B. Right, well, our distance is going to be 10 meters, obviously, but our displacement is going to have direction as well, magnitude and direction. So the magnitude component is 10 meters. Now, what's the direction? Well, the direction is towards B. It's to the right. It looks like it's to the east. We would just say it's 10 meters east. That would be our displacement. Now let's add another component to this problem here. Let's say we walk 10 meters to B and then we walk 10 meters back to A, back to our starting point. Right, so our distance, well, we traveled 10 meters to B and then we traveled 10 meters back. That's going to be 20 meters distance. But what's our displacement? Well, let's look at the definition here. An object's change in position, measuring from starting to final position. Well, if we go back to A, our starting and final position are going to be the same. Therefore, we have no displacement and no direction. So that kind of gives you a good idea of how displacement is different from distance. Okay, so now on to velocity and acceleration. These two are quite common terms in all branches of physics. But dealing with motion, we have the definition. Let's start with velocity, the rate of change of distance. This makes sense. It's like speed, but we have direction as well. There's two key terms in here that are going to help us a lot in dissecting this definition for our formula and such. It's rate and change. The term rate in any physics definition of a value or whatever, the term rate is going to tell you straight away that time is going to play a factor. And always it's something per unit time. You cannot have the term rate without it meaning per unit time. So if we want to find the rate of something, it's going to be something, in this case distance, divided by time. So we can write an equation here, be as distance over time. But we're not done yet. That's just how the term rate helps us. We know it's over time and it's distance in this case. Now with the term change, now if we want to, let's say we look at this equation as is right now. The velocity of something is the distance over time. That doesn't really make any sense. The distance when, or the time when, we don't really understand this. So this is where the term change helps us. The term change means the velocity is going to be the distance and time in a reference from another time or another distance. So that might be a bit confusing, but I'm going to make it a bit easier to understand here. When we have the word change in a definition, we're going to add the delta letter, which is a Greek letter. And this tells us that there is a change happening. The velocity is the rate of change of distance. So there's a change in distance over change in time. And this will make a bit more sense in a couple minutes when I get into the graphs, but just bear with me. Change in distance over change in time. Now if we want to simplify this into the fundamental units, we can quite easily. What measures distance? Meters. And what measures time? Seconds. So here's our formula for velocity. We're going to simplify this even further to ms minus 1. Now I talked about this a bit last video, but I'm going to again. If you don't quite understand how this equals this, you'll catch on quick. Pretty much you just need to know a negative exponent means you're going to divide it by the other variables. So here's our formula for velocity, ms minus 1, that's in fundamental units. If we want just the concept really, it's change in distance over change in time. Okay, now into acceleration. The rate of change of velocity. Alright, we have rate again, and we have change again. And it's pretty much the exact same formula for velocity, but it's the change of velocity, not the change of distance. So, acceleration equals the rate. Okay, so we have the term rate. Straight away, I'm going to put on the bottom t. Sorry, ignore that. And then the word change. So, yeah, it's a change in time. Now it's the change of velocity, so we want the change of velocity. Alright, so there's our formula for acceleration. Now let's simplify this into fundamental units. Let's start with t first. T is seconds, so it's just going to be seconds. Now velocity, well we have our formula for velocity here, so we might as well just plug it in there. Okay, so this is a bit messy. We're going to simplify this again to ms minus 2. So there we go. There's our formula for acceleration, and there's our formula for velocity. And we're going to use these formulas specifically for graphs, like this one here. So before I start with this graph, I'm going to make a simpler one, just quickly. Hopefully the line is straight. That's straight enough. Alright, so let's just make a simple graph first, just to kick things off. So let's say we're going to make it a velocity time graph as well, like the one below. Let's say I'm in a car and it's going 10 meters per second constantly. Ooh, that line's meant to be straight. Please assume it's straight. And we want to find, let's say after it goes 10 meters per second for 2 seconds. And we want to find the acceleration and the distance traveled. I forgot to mention, with graphs in motion, there is always graphs being made because it not only visualizes an object's motion, but we can find from the graph the other missing 2 components. So usually, or always actually, time will be on the x-axis, and then you can choose distance, velocity, acceleration, any of those three on the y-axis. And then whatever one you pick, like the velocity is chosen here, you can find acceleration and distance. The other two you didn't use from the graph, and I'll show you how to do that right now. So let's say this is a velocity time graph, which it is. I'm in a car, it's going 10 meters per second, and it's not accelerating, it's staying at 10 meters per second for 2 seconds. Okay, so we know the velocity is obviously 10 meters per second. What's the distance traveled? Okay, well, let's use the formula. We didn't make a formula for distance, but we can right now. Here we have change in distance equals change in t over, v equals change in distance over change in t. We can easily rearrange that to v times change in distance, times in change in time equals change in distance. So let's plug in the variables. Well, v is 10. Now, it's 10 throughout the entire 2 seconds, which is what we are finding it for. If there was an acceleration, a change in velocity, like there is here, we would have to find the average, because we couldn't use just some random value at 1 second or 2 seconds. We have to find the average. So luckily this one's easy enough. It's staying at 10, so the average is gonna be 10 meters per second. And we want to find how far it's traveled after 2 seconds. So the change in time, we want from 0 to 2 seconds, is just 2 seconds. And so we've got very easily here 20 meters. Now we could find this another way, but I'm going to go into that later. Now we want to find the acceleration. Well, we know the acceleration is a change of velocity. If the velocity is constant, there is no acceleration. And pretty clearly, although my drawing was bad, the line is straight. There is no change in velocity, which means there is no acceleration. Okay, now let's go into this graph here. Again, it's a velocity time graph, and we want to find the distance traveled and the acceleration after. We'll do 2 seconds again. Okay, so we have our formula for distance, change in distance, which is v times change in time. Okay, so we need to find the average again. So let's see what we've got. So the average velocity after 2 seconds is 10. It's very nicely laid out. It's a linear graph. The average of 20 divided by 2 is 10. So we have 10 times, we're doing it 2 seconds. And so we get 20 meters again as our distance traveled. Okay, now let's find the acceleration. So we have the formula right here. Change in velocity over change in time. Now this might trip you up, but we need the change in velocity, not the average velocity. This is very important, the change in velocity. So the change in velocity, if we have a time we want it after 2 seconds, the change in velocity is 20 meters from 0 to 20. So we have 20 meters per second over the change in time. We're finding it after 2 seconds. So the average acceleration is 10 meters per second squared. That might trip you up, but you need the change in velocity, not the average velocity. Okay, now I'm going to talk about other ways of finding the acceleration, or the distance in this case. The other way you could do it, and the much easier way, for me at least, is by using distance, velocity, and acceleration's mathematical connection. And what I mean by that is this line here in this velocity time graph, the area underneath the line is the distance, Now this is very important. You should write this down or memorize it, because you're going to want to use this, because you're going to come a lot of graphs like this, and if plugging into the formula is confusing, or if you just want to double check your answer, you know how to do this by remembering that the distance underneath a velocity time graph is going to be the area underneath the velocity time graph is the distance, and the slope or the gradient of the line is going to be the acceleration. So let's confirm this. We already solved. Let's just double check. So we solved what the acceleration is, and we solved what the distance was. So in two seconds. Okay, so let's find the area under the graph. Now you don't need to be a geometry whiz, but you need to know that for a triangle here, a right triangle, so we've got, it's going to be base times height divided by 2. That's how you find the area of a triangle. So this is the height, which is 2, and then the base is 20, right? And then divided by 2. And, well, these cancel out, and we're left with 20, which is what we got here. Okay, now let's find the acceleration. Well, like I said, it's the slope or gradient. So let's see here. So in this amount of time, it's rise over run. So we have a rise of 20 and a run of 2. And that's 10. So there you go. Confirmed. Use the area under the curve, or AUC, to find the distance when you have a velocity time graph, and find the slope when you have to find the acceleration. I'm just going to map this out a bit better for you to see. Sorry, just give me a sec. Let me just get rid of all this. Just to visualize it a bit better, I'm going to write D for distance, V for velocity, and A for acceleration. Now, if you have let's say you have, yes, a velocity time graph. If you want to find the distance, you've got to find the area underneath the curve, or the line. If you want to find the acceleration, if you want to go to find the acceleration, you got to find the slope. Same with if you have a distance time graph and you want to find the velocity, you've got to find the slope. If you want to find if you have an acceleration time graph, you want to find the velocity, you got to find the area under the curve. I think you get where this is going, but you see how they are related. Now, finally, we have these 9 graphs here. So this is just to give you a better picture of the types of graphs. So you see there's 3 columns here. One's a distance time graph, one's a velocity time graph, and one's an acceleration time graph. These are the most common types of graphs you'll come across, and it pretty nicely lays out the types of motion. So an object that is not moving, right? So it's stationary. That's what not moving. That's what stationary means, not moving. It's time, as time goes on, its displacement or distance is going to be the same. It's not going to be changing because there's no movement. Its velocity is going to be 0 because it's at rest, and its acceleration is going to be 0. That's pretty obvious. Now, if we find, uniform motion. Now, what uniform motion means is that there is no acceleration, or something is moving at a constant rate. There is no acceleration, there's no deceleration, it's moving at a constant rate. As you can see here, if something's moving at a constant rate, well, it's definitely going to have an increase of distance or displacement. It's constantly going to be moving. So yes, it's going to have a linear rise here, and just like our graph over here, if it's not accelerating, it's straight, and then obviously it's not going to be accelerating. And again, you find if you find the slope of this graph here, the slope's going to be constant, and what a surprise, it's a constant value. Lastly, we have motion with constant acceleration. So if you have a distance time graph and you have a curve, that's going to indicate acceleration, which makes sense because if the distance is increasing exponentially, it's not going to have a constant velocity. It's going to have an acceleration. And then as you see here, velocity is linear, increasingly, and so you kind of understand the correlations here in all three. And so pretty much I just want to stress how you can easily find the other two variables. If you have a velocity time graph, you can easily find the other two. Acceleration graph, velocity, you can find velocity and displacement. You understand. So I'm going to leave on that note, and next we're going to talk about the Suvat equations, as they're called. It's a bit more arithmetic, which is not the most fun, but yes, that's going to be next video. So thanks for watching. Like and subscribe and share this video with anyone that needs some physics helps.